Hello, and welcome to Chapter 1, Section 3, Part 2. So today we are finding limits using special limits, but with these special limits, we can't really use them until we know the basics of the properties of limits. So that's where I want to start today. So properties of limits kind of like is if you already knew what the limits are, there's little shortcuts that we can use to try to, if we were to complicate the original functions, it'd be easier to find the limits. And so like with this first property, if we knew the limit for f of x when x approaches some number c, I don't know, if that equals L, and if we knew the limit for g of x is k, then for this first property, if we were to try to complicate f of x by multiplying it by a constant number, some number b, then the limit, instead of having to find the overall limit and use one of our methods that we talked about, we can just multiply the limit with the constant that it was multiplying by. So it makes things a lot easier and simpler. Or another example is if you were trying to add or subtract your two functions, you can just add and subtract their limits. It makes things easier. So I want to do examples with you, that way you can kind of see how this is used with actual numbers, because it looks complicated now, but it's really not. So let's pretend that for some limit as x approaches c, we'll call it f of x. Let's actually pretend that f of x is the function x squared. And this equals 3. I don't know, I'm just making up numbers here. And then let's pretend we have another function, limit, as x approaches c of g of x, where let's pretend g of x is I don't know, the cube root of x or something. And let's pretend that's 8. Again, just making up numbers. Okay, so knowing these two limits, then if we were trying to find, say, the limit as x approaches c of 5 times f of x, then we already know the limit for f of x is 3. So really all I have to do is just take the 5, the constant that was being multiplied, and multiply it by my limit, which is 15. Or let's say I'm trying to find the limit of my two functions being subtracted. Okay, well, f of x minus g of x would just be x squared minus cube root of x, which is, I don't know, doesn't come out very nicely. But if I'm trying to find the limit of those, then rather than having to plug stuff in and whatever, I could just subtract my two limits, because the limit for f of x was 3, and the limit for g of x was 8. So it makes it a lot easier because I'm just subtracting limits. So that's from the second property where we can add or subtract, and it works both ways. We can do this multiplying or dividing. Let's pick dividing. So if I divide the two functions together, then I can just divide their limits. 3/8 is a fraction, doesn't simplify anymore, so our answer is 3/8 for the limit. Or we can raise one of my limits to some power. So if I'm trying to do f of x cubed, rather than doing my f of x, which was x squared times x squared times x squared, I could really just cube the limit. And then I get 27. So much faster. And the last property is talking about those composite functions like f of g of x. For those, we're basically saying, rather than trying to plug in g of x for f and then solve it from there, just take the limit of whatever's inside. I just realized I wrote my last property wrong. So this is supposed to be a k, because k is the limit for g of x. So we start with our inside, whatever's inside the parentheses, because, PEMDAS says do parentheses first. So we're really just looking for the limit of g of x, which we know was 8, and then plug that into our f equation. So when we're finding the limit here, it kind of eliminates the need for us to find f of g of x entirely, because f of 8 would just be 8 squared, which is 64, and then that's it. So knowing those limits, or those properties of the limits, helps us use our special limits better. So our special limits are going to look like this. We've got 3 of them. The first one is the limit as x approaches 0 of sine x over x equals 1. So these are special because somebody out there came up with this answer for the limit through like proofs and stuff. So I'm less interested in that. I'm more interested that you know how to use these because these special limits are how we're going to like kind of simplify and help us kind of like one of our methods for solving limits. And so like we wouldn't be able to use any of the methods that we've learned so far. Like you can't just plug this in because you would end up with 0 on the bottom and that's not allowed, things like that. So that's why we can't just figure these out ourselves, and that's why they're special. So if we remember our rules then for our special limits, as long as you see something with sine x over x where your limit is approaching 0, it's always going to equal 1. Or if you see something like 1 minus cosine x over x, where the limit is approaching 0, that limit is always 0. This third one we use less often, but if you ever see it, just know that it equals e. So let's do some examples with these. Because with these limits, even though we know what the numbers are, we still have to be able to use them to simplify others. So let's say we are trying to find the limit as x approaches 0 of tangent of x over x. Okay, so clearly tangent of x over x doesn't look like any of the ones that we've had so far. However, I can rewrite tangent of x as sine over cosine. Okay. But this is ugly right now because I got fractions on top of fractions. So let me rewrite this so it looks a little nicer. So I'm going to rewrite this as the limit approaches 0 of sine x over cosine x times 1 over x. Because if I'm dividing by x, then this is the same as multiplying by its reciprocal, or 1 over x. Or if you want to think about it as keep, change, flip, we've kept the first fraction, flipped the sign into multiply, and then flipped changed the sign into multiply and flipped the second fraction, or the denominator, which is x over 1, so it changed into 1 over x. Okay, because if I write it this way, I can kind of see that I'm going to end up with like sine x over x, and that allows me to use the first property. So if I rewrite this into, I'm just going to reorder some things. So I'm going to change it so that I have sine x over x, and then it's going to get multiplied by 1 over cosine x. Okay, well, using our properties, we have 2 things being multiplied. We know the limit for sine x over x as x approaches 0 is that special limit where it equals 1. Okay, so we know this part just equals 1, and then we just need to multiply this by the limit as x approaches 0 of 1 over cosine x. Well, 1 over cosine x is, when you plug in 0, you don't get 0 on the bottom because cosine of x is 1. So that just equals 1 if I just plug in. And then finally, 1 times 1 is just 1. So the limit as x approaches 0 of tan x over x is just 1. All right, let's do another example. This time, let's do the limit as x approaches 0 of 2 minus 2 cosine x over 3x. And hopefully, just looking at this problem, you can kind of tell it kind of looks like the second special limit because the second special limit has that 1 minus cosine x on top, and we kind of have something like that on top. So let's kind of simplify this a little bit. If I factor out a 2 on the top, then I can get it to look like the 1 minus cosine x. And then, again, I'm going to rewrite this fraction so that I can kind of get that 1 minus cosine x over x by itself. So I can take out that 2/3 and just write it in a separate fraction. And now I have that 1 minus cosine x over x from this part right here, and this 2/3 I'm just leaving it separate. So this kind of looks like that first property where I have a constant being multiplied to the limit. So really I can just take that constant of 2/3 and multiply it to the limit of 1 minus cosine x over x, which is just 0. And 0 times anything is always 0. There we go. Okay, let's try slightly more complicated now. We're going to do the limit as x approaches 0 of sine of 4x over x. Ooh, okay. So this kind of looks like our first special limit. Almost, but not quite. Because I have that 4 there in front of the x on top, whereas the special limit didn't. So because it doesn't quite look like the first special limit, I want to kind of manipulate it so it does look like it. So in order for us to use the first special limit, we have to have the same variable on top as on the bottom. And so right now I have a 4x on top, which means if I could make the bottom of 4x, then the special limit would work, because then it's like the same thing on the top and the bottom. So what I'm going to do, it's kind of tricky. I'm going to multiply this by 1/4. But of course, I can't just like multiply something by 1/4 because that changes the value of it. So if I do something like multiply by 4 over 4, then that'll give me the chance to change the bottom into 4x. But really, I'm just multiplying by 1, so I'm not going to be changing the value of anything. So if I were to rewrite this, this would look something like this. It would be 4 times sine 4x, where that first 4 was from me multiplying it by the weird 4 at the end. But then I'll have the 4x at the end, or at the bottom in the denominator. Okay, because now I have sine of 4x over 4x here, and that limit will just equal 1. But then I still have that 4 in front. So this will end up being, because I'm just multiplying by a constant of 4, it'll be 4 times 1, because 1 is the limit for sine 4x over 4x. So my final answer is just 4. That's a weird, tricky one, just because it looks weird. I'm going to do one more, kind of like it, so we can get used to it. So again, limit as x approaches 0. This time we're going to have tangent of 4x over 6x. Okay. Okay, so kind of like that first example we did here with the tan x over x, I'm going to rewrite this as the limit as x approaches 0 of sine of 4x over cosine of 4x, because that gives me tan of 4x all over 6x. And then again, let me simplify this so that I have not like crazy complex fractions here. So I'm just going to multiply this by 1 over 6x instead of dividing by 6x. Okay. And then kind of like that first example that we did, I want to kind of make it so that I have the sine 4x over 4x again. So let's rewrite this. I'm going to start by just splitting up that 6x into sine of 4x over x. So I'm just putting this x from the 6x underneath. And then I'll multiply the 6 along with the cosine 4x. That was all on the bottom. Okay, so this sine of 4x over x kind of looks like what we just did with this problem up here. So I'm going to multiply everything that I have right now by 1, because 4 over 4 is just 1. But because I'm doing 4 over 4, then I can change this bottom x under the sine x, or under the sine 4x, to be sine of 4x over 4x. So that's where this 4 went. But then this fraction here, I'm also multiplying by the 4 that's on top. And then I have the 6 cosine 4x there again. Okay, so now we know this part of our limit just becomes 1, because that's the special limit. Then we're multiplying by the limit as x approaches 0 of 4 over 6 cosine 4x. Well, here, it's not a special limit, but I can plug it in, because if I plug in 0, I don't end up with 0 on the bottom, since cosine of 4 times 0 is just cosine of 0, which is 1. So I end up with 1 times 4 over 6 times 1, which is just simplifies to 2/3 when I multiply all that together. And that's it. Those are all the examples I've got for you. And that's it for our section 1.3. Thanks for watching. Bye-bye.